Hello everyone, my name is Ádám István Szűcs and we'll talk about GPU testing. So I think first, let's put this into context. I will tell you a story about the startup and its code base. So basically we had 6 months to deliver a rendering engine which is capable of rendering volumetric and triangulated data as well. And it was mandatory to have a global illumination implementation in our solutions. So summarizing it, we had to have a really good visual fidelity and we needed to assure that good quality of rendering. So in general, let's take a look at how just a simple GPU development pipeline looks like. So first, the GPU developer always thinks about shaders or GPU code, or it can be OpenCL or CUDA or any type of GPU language. But most of the time, the execution model is always the GPU when the GPU developer thinks about. And also, the GPU by itself is not just alone in the machine. It needs to be told how to execute and what to execute on itself. So therefore, execution of shaders and data management most of the time are implemented by API calls, which are wrapped in big game engines, for example, in Unreal Engine or CryEngine. So basically, when we think about an algorithm which solves a problem, most of the time they cannot directly fit into the GPU. They need to be sliced down in such a way that they fit onto the CPU and the GPU, and they need to communicate to each other, and they need to execute the algorithm itself to solve the final problem. This is all good and nice, but the biggest problem of that is there's no direct techniques to assure quality in the early stages of the development cycle when the solution contains graphics and compute as well. So let's see how it looks like when we have some really good graphics or when we have graphics in our program or product. So for real-time rendering, we have 16 between 33 milliseconds per frame, which is really a tight schedule. So therefore, we will need to feed the GPU well, and we'll need to execute the shaders in a really efficient way. The CPU and the GPU works together, and also what we know is the GPU is really powerful. It can execute millions of threads concurrently, and it can solve big problems, but it's not all powerful. Not all sub-problems can be transformed in a way such that the GPU will be efficient in solving them. And also, a big problem when developing GPU products with GPU solutions is that the programming model needs to be changed when moving from the GPU to the CPU. However, we might see some big CPUs. I think it's EPYC 2 will have 64 cores, which is almost close. I mean, not that far away from a GPU, but still, they're two different programming models. And also the problem with that is GPUs can be really mysterious because the scheduler inside the GPU is hidden by the driver, and it not always can be tamed real well. So let's see what type of problems can we face when we develop something which contains graphics. As you can see in this image, some things can really go wrong, which it should have been a statue of a horse, but I don't know if you can really identify a horse from that picture. So the type of errors that we can get is we can get blank screens, we can get corruption, we can have some flickering, and also we can have some shader bugs. So shader bugs are the most interesting things to have. Alistair had a nice paper about it. They basically tested OpenGL drivers where they found out that in Melee OpenGL drivers there were many errors. So therefore, shader bugs can be caused, or so to say, or rather driver bugs to say. And another problem is the performance. So why we're porting something, or why we are implementing something on the GPU is because we want to have fast execution, but sometimes we are not really getting it. We're just gonna get slowness, flickering, and corruption at the same time. So what are the main problems? The main problems is the GPU code goes through a driver, which is not open sourced, at least on Windows, because we know that in Linux we have the open sourced AMD driver, and also we have the RADV driver, which are open sourced. But we would like to approach a cross-platform. We would like to have a cross-platform product, so therefore we need to deal with the Mac and also the Linux environments as well. And also the programming model needs to be changed, and also there are no techniques to assure the quality early in the development life cycle. We have some tools, but they are most for post-mortem analysis. So therefore, you will be in the situation where you have some error, and then you will inspect it with some kind of tool, for example, RenderDoc or Radeon GPU profiler or analyzer as well. And what complicates the things is if you're developing shaders, you will have multiple compilers as well. So you will have a DirectX compiler, GeoSlang, a cross-shader compiler, and all kinds of things. So I think the best thing to overcome these problems is to always take a look at the shader playground online. This is just the godbolt of GPUs. So this is a really nice and handy tool when one is developing GPU shaders. So let's see what we can do about this whole GPU testing thing. What is the current state? So the current state now is early in the life cycle is impossible to deal with the testing. And only the solutions are for the final rendered images are analyzed with artificial intelligence or manual inspection. But the problem with that is this is not the failing early principle. So since we're talking in the context of Vulkan, thankfully we'll have SPIR-V, which is standardized, and it's cross-platform intermediate binary representation, which is good because we'll be able to address all the main operating systems, and we'll be able to object different architectures such as ARM or desktop or any type of GPUs. But it's all nice and all good. But like how we basically run something on the GPU which can be tested. So the more natural way of transforming these shaders in such a way that they can be tested. Then there's a tool called SPIR-V Cross, which has an experimental C++ generation engine, which basically can generate a C++ equivalent of the shaders you've written using the OpenGL math library. But I think it's still in experimental state, so therefore sometimes it can generate incorrect code. And also if you have a large system, a large rendering engine or a large simulation engine, it won't integrate well by itself, by default. And also it doesn't help with generating the, so to say, boilerplate API calls in Vulkan, which are really explicit, so to say. And I think there will be a presentation about the first few steps with Vulkan, which will show you that how many lines of code is needed to render a simple triangle with Vulkan on the screen. So therefore, we'll need to have some kind of mechanism to generate these API calls. And also does not help with the resource management, which means does not automate any kind of allocation or optimization between resources in the schemes. So therefore, what we did is we extended SPIR-V Cross, and we generated our necessary types in our type system. So basically, we generated all the types for the rendering hardware interface statically. So when we start to build our software, which was a C++ system, having GLSL or HLSL shaders, what we did is basically we did reflection, generated all the resources from the shaders, and then with this, basically a simple shader become a class or multiple classes with its types and structures exposed. And it was all nice, but what can we do with it? So like now we transformed the problem of going straight on the GPU to basically a software renderer because now we are on the CPU. So to handle this kind of problem of arranging all this code, we used some kind of paradigm in game engines known the frame graphs, which is basically DAG having data and operations represented as a graph and their interconnections between themselves. And what the programmer, so basically with the statically generated classes or operations from the shaders, the programmer simply just connects these shaders to each other, and then the system automatically can optimize all the things that would be done by manual programming. But so what was the result of this whole methodology? We had a simplified resource management because we were able to handle the transient resources in the frame graph, because basically we had a graph optimizer which traversed the whole graph of the render passes, or if we would see a superset, we could call it the skein. And then we had a simplified rendering and compute pipeline, which was more general, so therefore productivity was increased by a lot. And also the good thing was that since we've generated all the shaders to C++, we had a fallback state. So we had some kind of a debug mode in our old rendering graph, which was basically running the shaders in the C++ mode, and we were able to unit test all our shaders early in the beginning, which was quite beneficial in the end. But it's all nice. We have, so what we have now is we have the generated C++ shaders. We can test them, and it's all nice. But now we have real-time ray tracing. It's quite here. So I think the problem would be running this generated real-time ray tracing equivalent shaders in C++ would drive us to the levels of a Disney or Pixar leveled renderer, which is hard to solve in small scenarios, such as in a startup environment. So therefore, we should do something about this. Also taking into account, there's also another problem, which is the execution mode is not the same, so we cannot assure that we are executing the same piece of code, because this is just a generated C++ code out of the shaders. But still, we can catch a few problems early. So what can we do about it? We'll need to move the whole thing up to the GPU. So the best would be to have the testing on the hardware, not just some kind of software renderer. And also, so the base motivation for it needs to be as fast as possible. So this is how I think about our current solution. We want to go for an air conditioning, but we had something else instead. It works, we get cool, but still we would need to move on a little bit. So, and also we didn't have that much of a big code base, so we had a few 100,000 lines of shader code. But in bigger systems with large material systems, many shader permutations, this could take much more time in the whole tool chain, which can cause really slow reiteration times in the shaders themselves. So basically, compiling all the so not just compiling all the shaders takes lots of time, but like converting them and then compiling them in C++ would take much more time. So that's also another problem. Another problem is that we have many extensions in Vulkan. So we have around more than 150 extensions now in Vulkan, or even more, which would need to be tested as well, because in games and in optimized scenarios, for example, if we are optimizing on a simple AMD, for example, on the new Navy GPU, and we would want to have all the performance inside it, we would need to use extensions. Therefore, we'd need to test those extensions as well in the shaders. So what kind of solution we could do? We could move up the whole thing to the driver, but the problem of that, they're not open sourced on all the platforms, how I mentioned. We have Radwe, but it's only working on Unix environments and only on AMD hardware. And so therefore, what about NVIDIA? What can we do with other vendors? That's also a problem. So to move the whole thing up to the driver, we would need a cross-vendor collaboration, which would be a bit hard to achieve, I think. So we need to do some kind of round trip. We cannot implement it in the driver. Software renderer does not solve all the problems. It can help in finding smaller bugs and problems, but still we'll need to go forward. And I think the best solution would be which we need to work on, is there's a thing called validation layers in Vulkan, and Lunergy is one of the pioneers in developing such layers for Vulkan. And I think the best would be to have a GPU-assisted validation layer, which basically runs all the things on the GPU in such a way that basically it's gathering all the debug information in a buffer object in the shader, which is, so to say, patched into it with the SPIR-V optimizer to handle the own GPU execution. With this, we could achieve it, but how can we achieve it? So developing a simple layer would be a bit time-consuming from the ground up, but thankfully Lunergy has the solution, which is called the layer factory. So with the layer factory, we can implement something on the GPU. So therefore, we could have a thing called VK assert. So we could have assertions and unit testing and shaders executed on the GPU, which has all the extensions and the programming mode. So I think, thank you for listening, and thank you for AMD for providing all the hardware and solutions for the presentation.
Okay, any questions from the audience? If no, I have many, but I try to resort to one, which is blatantly self-motivated. Would it simplify the development and testing and debug process if you could write your shaders in a similar style that you would write CUDA code, for instance, like a single source, and it is all in C++, and the compiler takes care of generating the SPIR-V and the code to invoke it?
So SQL would be cool. I think SQL is something that we're talking about. It's really good. The only thing that I don't know about it is that can it do graphics, or if it needs to interrupt with graphics, for example, with Vulkan, which would be also good. But what I've seen from the early days of OpenCL, interrupt with OpenGL was a really hard thing. So therefore, I think if we would have a C++ environment and we could write all the things in C++, I mean the graphics and the compute as well, that would help a lot, I think. Also the problem of shader development is that we have just dialects. So GL slang also tells that the OpenGL slang, which really describes how the language is built, or high-level shading language. So I think having a C++ syntax for writing shaders and the host code as well, that would be terrific, I think.
Okay. Anyone else inspired for a question? If not, then let's thank our speaker again.